Assalamu alaikum everyone. This is Shamroz Khan from Mechanical Engineering Department of NED University of Engineering and Technology, and my partner Faizan Ahmed. He is also from Mechanical Engineering Department of NED University of Engineering and Technology. The topic we are discussing today is a practical feed-forward control mechanism. This topic is related to the autonomous underwater vehicles. These vehicles operate without any human interaction and they operate with the help of computer input. So feed forward control mechanism, it is basically a speed control mechanism that is designed for the purpose of controlling the speed of the underwater vehicle at a desired value. It is based on self-propulsion estimation model. So here we have a block diagram of this feed forward control mechanism. We will discuss this in a while. Now discuss self-propulsion estimation model. So self-propulsion means that a vessel is moving with a constant speed. So self-propulsion estimation model is basically built on empirical relations suggested by the IMO and ITTC. So it considers the interaction between the underwater vehicle and water. Let's consider a vessel that moves inside the sea. It will encounter some resistance, and that resistance has to be overcome by the thrust. That thrust will be generated by the rotating propeller. So our self-propulsion estimation model will predict that rotation rate which is required for our desired velocity. So it is an iterative process. So we will first input some velocity model parameters and an arbitrary rotation rate, and that model, with the help of these relations, will find the resistance and the thrust. Now this is the flowchart of the self-propulsion estimation model. So after the resistance and the thrust has been determined, and this model will now compare the thrust and the resistance, that whether the thrust has overcome the resistance or not. So this is the condition, and if this condition is not satisfied, then further iterations will be done until we finally achieve the required rotation rate for our desired velocity. So that rotation rate will be termed as predicted rotation rate. So this will be the main output of the self-propulsion estimation model. Next, we calculated the total resistance and the propeller rotation rate for DARPA sub-off, which is also an underwater vehicle considered in this study, and we plotted its results with respect to velocity, and then we compared the results of self-propulsion estimation model with the experimental and the numerical observations. And what we observed, that the results obtained by the self-propulsion estimation model are very accurate, that they have a good agreement between them. So this was all about the self-propulsion estimation model, and now my friend Faizan Ahmed will now discuss the feed-forward control mechanism. Thank you.
Thank you, Shamroz. I'll take it from here. So now that we have discussed the self-propulsion model, it basically accounts for the hydrodynamic interaction of an underwater vessel. We shall discuss the developed speed control system and see how it utilizes the aforementioned model. This is the flow diagram of the speed control system, which shows the main blocks, their respective sub-blocks, along with the required inputs and the resulting outputs of the entire control system. The feed-forward speed control system consists of two main blocks: the propeller rotation rate control block and the ship dynamics block. The rotation rate control block is based on the algorithm enclosed by the red box, while the basis for the ship dynamics block is the self-propulsion estimation model. The propeller rotation rate control block increases the propeller's rotation rate in an iterative manner after short time intervals. The resulting values are sent to ship dynamics block to calculate thrust. The main functions of the ship dynamics block are to estimate the resistance encountered by the underwater vehicle at a particular speed, to calculate the amount of thrust using the value of rotation rate provided by the rotation rate block, and to compute the velocity of the underwater vessel using the values of resistance and thrust. Now we look at the necessary inputs and the main outputs of the feed-forward control system. The inputs are the mass of the underwater vehicle M, the added mass mx, which is the mass of water moving with the vehicle due to no slip condition, the target velocity vt, which is the velocity we want the vehicle to achieve, the initial velocity of the vehicle v naught, and the initial propeller rotation rate n naught. The main outputs are the rotation rate of the propeller n, the corresponding thrust produced t, the resistance encountered by the vehicle rt, and the vehicle's velocity v. These output quantities are calculated in every iteration. Now that we have discussed the main functions of the blocks and the inputs and outputs of the speed control system, I shall now discuss how the system actually works. A suitable time interval is selected for the iterative process. After every iteration, the elapsed time increases by selected value of time interval. In every iteration, rotation rate block increases the value of rotation rate. Using the value of rotation rate, the ship dynamics block calculates the corresponding value of thrust as well as resistance and speed in each iteration. The vehicle's speed is calculated using the equation shown here. When thrust and resistance balance each other, the iterative process stops. This point is said to be the steady state of the control system. For verification of the speed control system, forward motion of DARPA sub-off an underwater vessel is simulated and its speed is maintained at the desired values of 4 meters per second and 7.5 meters per second by employing the feed-forward speed control system. The values of the required parameters for the control system are tabulated here. First table contains the physical properties of water used in the simulation. Second table includes the physical properties of DARPA sub-off. The results obtained from simulation are presented in a graphical form. They are rotation rate versus time graph, thrust versus time graph, resistance versus time graph, resistance plus thrust versus time graph, and velocity versus time graph. Here we shall only discuss the velocity versus time graph. It can be observed from the graph that the velocity in the beginning increases with the passage of time and reaches a constant value which is close to the desired values of 4 meters per second and 7.5 meters per second. Simulation results are also presented in a tabular form. The table contains the steady state values of the output parameters of the control system. It is worth noting that for the desired speed of 4 meters per second, the steady state velocity comes out to be 4.018 meters per second with a steady state error of 0.4%. And for 7.5 meters per second desired speed, the steady state velocity is 7.491 meters per second, having a steady state error of 0.1%. Now I would like to highlight some benefits of the developed feed-forward speed control system over the conventional feedback speed control systems. Number one is that it accurately accounts for the external disturbances before they get a chance to disturb the speed of the vehicle. Secondly, it does not require any underwater sensor for its operation. This is a good thing because these sensors are quite expensive. And lastly, it reduces fuel consumption while increasing the service life of the AUV due to smaller reaction time in achieving the desired speed. All these benefits make the feed-forward system economically more viable than the conventional feedback systems. So is the newly developed feed-forward speed control system a good choice for AUV? Well, the simulation results clearly show that this system is capable of maintaining the speed of the AUV at the desired value. Moreover, the advantages it has over the traditional speed control system makes it an attractive solution. Therefore, it can be concluded that this system is indeed a practical choice for the speed control of an AUV. I will end my presentation with an inspiring quote from one of the greatest scientists in history, Sir Isaac Newton. He said, "No great discovery was ever made without a bold guess." I thank you all for your time. This is Faizan Ahmed and Shamroz Khan signing off. Take care of yourselves. Allah Hafiz.